Molecular orbital theory. Molecular orbital theory, sometimes abbreviated MO, calculates orbitals for the entire molecule instead of just for atoms. So my husband was telling me some stuff last night. It was actually kind of interesting. There's chalk stuck in the drain down here. Maybe there's a squirrel. Think about a child splashing in the bathtub, making waves, right, in the water. And the waves bounce around. If you put two children in the same bathtub, right, what's going to happen with the waves? They're going to overlap and affect each other, right? The waves are not going to stop in the middle of the bathtub just because there's two children in there, which is a source of many arguments, actually, of splashing, and you splashed me, and you're taking up too much space. But there's an interaction between the waves caused by each child. In the valence bond theory, we talk about hybridizing the orbitals of one atom, but those orbitals do not affect what's going on with the other atom that it's bonded to. So what molecular orbital theory does is it looks at orbitals for the entire molecule. For all the children in the bathtub or the swimming pool or whatever container they are in and splashing around. They are all going to affect the waves of the other people in there. So we're going to just talk about the math behind this. The Schrodinger equation is what describes the orbitals for an atom. And solving the Schrodinger equation, even for a simple molecule like hydrogen, two hydrogen atoms bonded together, is impossible because the equation is very complicated. And so what they do is they use a trial function as an educated guess, and then they optimize. So it's basically an iterative process where you try something, and then you try something else, and is that better? Okay, let's keep going in that direction. And so they use computers to calculate the energy of that trial function using the Schrodinger equation, and they optimize it to the lowest energy. And so this is the best we can do, but we can never do better than nature. Nature does the best job of minimizing the energy of the orbital. So we make an attempt at describing these things, but it's not perfect at all. So LCAO, linear combination of atomic orbitals. This is a weighted linear sum of the valence atomic orbitals of the atoms in the molecule. And this is the simplest trial function for figuring out the energy that works reasonably well. And so that's what we're going to stick with, linear combination of atomic orbitals. So those atomic orbitals that we're talking about are the s and the p and the d and the f orbitals that we learned about. These are going to combine the atomic orbitals of all the atoms in the molecule. So we're not just looking at, in valence bond theory, we just looked at the central atom and combining its atomic orbitals to get a hybrid that kind of helped us explain what we were observing. Here we're going to take all the atomic orbitals of all the atoms of the molecule. And you can see how that can get kind of complicated. These linear combinations are delocalized over the entire molecule, whereas those hybrid orbitals are localized on a single atom. Up here we were looking at, I guess this one was water, right? The hybridization on oxygen. But this is localized on the oxygen atom only. These LCAOs are delocalized over the entire molecule. So that's an important difference between valence bond theory and molecular orbital theory. Let's look at hydrogen. So one of the molecular orbitals is an equally weighted sum of the 1s orbital from each atom. So if we take this orbital, and you can think of it as a geometric shape. It's really a wave function, but if we take this shape and we add it to this shape, we get something like this. And this is given the name sigma because of its shape. It's symmetrical around this line between the two atoms. And it's a sigma 1s. It's kind of small here, but there's its name, sigma 1s, because it comes from the combination of 1s orbitals. And this is called a bonding orbital because when we combine these two orbitals in this way, this energy is lower. Bonds only form if the energy is lower when that happens. If the energy is higher, it's not going to happen. Okay? So, any questions yet? We're taking these two shapes and combining them, equally weighted sum, linear combination of functions, and we get this shape. The next molecular orbital is where we take one 1s orbital as positive and the other as negative. Because remember, orbitals have phases. Remember I showed you with the rubber hose over here. We looked at the wave and it went up and down, and it has phases, up and down. And this orbital, because it doesn't have any lobes, we only see it as either all positive or all negative, but it's actually going back and forth. So if we take and we have the destructive interference, let's back up here. This is like the constructive interference of waves, and this is like the destructive interference of waves. We get this sort of a shape, where we have a node down the middle, and we have a positive over here and a negative over here. This is not a positive and negative charge. These are opposite phases of the waves. So the wave that I made with the tubing, there's above the axis, that's positive, and below is negative. So we have opposite phases. Is this going to contribute to bonding and holding these two nuclei together? No, because there's a node in the middle. This is not a bonding orbital. It's called an anti-bonding orbital. Alrighty. So when we combine these, the energy goes up, and this is an anti-bonding orbital. And so the name of this orbital is sigma star 1s. So sigma 1s was a bonding orbital, lower energy. Sigma star 1s is an anti-bonding orbital. Constructive interference gives us a bonding orbital. Destructive interference gives us an anti-bonding orbital. Any questions yet? I don't want to lose you right at the beginning. You were lost before the beginning. Okay. Well, at least you're honest, right? So this kind of summarizes. When we have two atomic orbitals added together to form molecular orbitals, the bonding orbital is going to be lower in energy. It's going to have high electron density between the nuclei. So here's constructive interference between these two waves, and this gives us something that's lower in energy, and there's a lot of electron density between the atoms, and that's going to hold them together. When it interacts destructively, we get an anti-bonding orbital. There's a node, a region of zero electron density between the nuclei. This is a higher energy condition, and this does not contribute to bonding the two atoms together. It's going to do the opposite. That's why it's called anti-bonding. So we're going to take our orbital diagrams that we had before, and we're going to draw molecular orbital diagrams. So energy is always going up as we go up the page. And now we're going to look at the interaction between these two atoms. Here's a hydrogen atom, and here's a hydrogen atom. So these are the atomic orbitals on each side. Each hydrogen atom has one electron. It'll be in the 1s orbital. So here's our 1s orbital box with one electron in it. And over here, we have a 1s orbital with an electron in it. This electron is going to have opposite spin because we're going to put these two guys together And you can't have the same spin in the same orbital. This doesn't work out. So when we combine the 1s and the 1s, we get 2 orbitals. The number of orbitals is still conserved. If you start with 2 orbitals, you end up with 2 orbitals. You don't get 3, you don't get 1. So this is the bonding orbital. It's lower in energy, sigma 1s. The anti-bonding orbital is higher in energy. And then we're going to take these electrons, and they're going to fill up the lower energy orbitals first. And so, because there's only 2 of them, they're going to go into this bonding orbital. Any questions? Does this make any sense? Kind of? So we have something we call bond order, which helps us to predict whether this molecule or this bond is going to be stable or not. And the bond order is the number of electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals, and then divided by 2. So for hydrogen, for H2, we had 2 minus 0 divided by 2. The bond order is 1. Let's go back to this diagram. We're taking the number of bonding electrons that contributes to the bond happening. We're subtracting the number of electrons that are in antibonding orbitals. Here there are 0. And then we're going to divide by 2. Think of it as an average. If the bond order is positive, you'll get a chemical bond that tells us that the energy is going to be lower. And the higher the bond order, the stronger that bond is going to be. If you get a 0 or negative bond order, then the bond's not going to form. It's not favorable energetically. So let's look at He2. Does He2 exist? No. Helium is not one of those diatomic molecules, is it? But let's see what would happen if we made this. So here's a helium atom, and here's a helium atom. Each helium atom has 2 valence electrons, right? In the 1s orbital. 1s orbital. When we combine these 2 1s orbitals, we get a bonding orbital and an anti-bonding orbital. Now there are 4 electrons, and we put 2 in here and 2 in there. And then to calculate the bond order, we take the number of electrons in bonding orbitals, we subtract the number of electrons in anti-bonding orbitals, and we divide by 2. So we have 2 bonding minus 2 anti-bonding is 0, divided by 2 is still 0. This is not predicted to happen, and it doesn't. How about He2 plus, an ion, a diatomic ion of 2 hydrogen atoms? Sorry, helium atoms. Well, we've got the same atomic orbitals to start with. We're going to end up with the same molecular orbitals, but now there's only 3 electrons. Because He2 plus, it has a positive charge because it's missing 1 electron. So there'll be 2 down here and 1 up here. So then to calculate the bond order, we take the number of electrons in the bonding orbitals, which is 2. We subtract this 1 electron in anti-bonding orbital, and we divide by 2. So 2 minus 1 is 1, divided by 2 is 1/2. That is positive. That tells us that this bond can form. It does. It's not a real common ion, but it does form. Yeah, this is a bond order of 1/2, meaning this bond is weaker than the hydrogen bond, which had a bond order of 1. But the greater the positive bond order, the stronger the bond is. Any questions? Other than where did Troy go? So summarizing, we are approximating the molecular orbitals as linear combinations of atomic orbitals. So I'm not a big fan of acronyms, but I'm not a big fan of writing out long words all the time either. So MO, molecular orbital, AO, atomic orbital. The number of molecular orbitals formed is equal to the number of atomic orbitals. If you start with 5 orbitals, you end up with 5 orbitals, okay? Orbitals are conserved. If you have 2 atomic orbitals combining to form 2 molecular orbitals, one's going to be lower in energy, one's going to be higher. Let's go back to this picture. If you took the energy of these 2 orbitals and averaged it, it would be the original orbitals, wouldn't it? One is above and one is below. So the overall energy is the same, it's just been split into 2 pieces, if that makes any sense at all. So after you draw the molecular orbitals and then you're going to fill them up, you're going to do the same thing that we did with the atomic orbitals, and you're going to fill up the lowest energy orbitals first, and you're going to do Hund's rule, which is put them in singly first with parallel spins and then pair them up, because they're still riding the public bus and they prefer to have a seat by themselves until they have to share. And in order to have stable bonds, we have to have a positive bond order. That means there are more electrons in the bonding orbitals than there are in the anti-bonding orbitals. So bonding orbitals contribute to the bond forming. Anti-bonding orbitals work against the bond forming. Yes?
Can you give an example of oxygen or fluorine?
We will get to oxygen and fluorine. It gets a little more complicated. Yes, it applies to ions and molecules. We are going to limit ourselves to a few diatomic molecules for our class, yes, which will be plenty. But yes, you can apply it to all molecules. It's never too early to be yawning. Use molecular orbital theory to predict the bond order in H2 plus. Is the H2 plus bond stronger or weaker than the bond in H2? So what we need to do is we're going to draw our little orbital diagram here. So this is just to remind us that energy is going up that way. So over here we have a 1s orbital from this hydrogen atom. And over here we have a 1s from that hydrogen atom. And each of these guys has 1 electron, right? We're going to draw this guy up, and we're going to draw that guy down. That would be H2. We are doing H2 plus. How many electrons would be in H2 plus?
0.
I heard 3 and I heard 0. How about 1?
Yes.
So one of these is the atom and the other is going to be an ion. So this is H2, this is H plus, which has no electrons. This one has no electrons. Yeah, the 0, you were just talking about this guy. And this is H with 1 electron. And I didn't mean to draw the H plus bigger, it just happened. So when we put these 2 guys together, we're going to get, that's a very sad square. No. Maybe I should do these instead. How's that for a square? Not beautiful? Yeah. Okay, now I have to do all of them like that.
Make sure they're equidistant from each other.
Yeah, that's easier said than done. Well, that's pretty close. But now this guy's too small. I'm in a mood today. Okay. Oh, that was kind of fun. The dotted lines now, though, horrendous. I can't do anything about this.
It's okay, we need flaws.
We'll do, I don't know. So what's the name of this orbital? Sigma 1s. And this guy up here? Sigma star 1s. This is the antibonding orbital, and this is the bonding orbital. So these are our atomic orbitals, and these are our molecular orbitals in the middle. So we have one electron, and then we're going to put him into our molecular orbitals. Which one are we going to put him in? The lowest one. So we're going to put him down here. We need to predict the bond order. How many bonding orbital electrons do we have? We're looking at these guys only in the middle. We only have one electron. So there's one electron in the bonding. This is bonding, right? How many electrons in this box? One. Okay, good. How many electrons in this box? Zero. 1 minus 0 divided by 2 equals 1/2. This is the bond order for H2+. Is that bond stronger or weaker than the H2? It's weaker, because H2 had a bond order of 1. Okay? Did you see what I did there? No?
I want to see an example with a bigger number. Yeah.
We're getting to it. We're getting to it. Yes, calm down. Settle down. Hold your horses.
Actually, I wanted to.
Period 2. Here we go. Period 2. And the balances are moving at us.
Oh, is it really moving? Is that what it's really?
Well, no,
Or is
it's
it like
it's
rotating
doing some
somehow?
adjustment, this self-calibration
Yeah.
thing. It really sounds like a cow, though, doesn't it?
Like one of those fake electric cows?
Yeah, or one of those little toys that you tip upside down.
Which one is it so I know not to use it?
No, they all do that.
Oh, they all do.
Yeah.
I use it anyway.
Or it's like walking, through Walmart at Christmas time, and there's always these, motion-sensitive dolls that start crying or jumping around when you walk past them. It's creepy. Creepy. The fish that sings, yeah. Okay, back to this. Period 2, homonuclear diatomic molecules. Strange combination of words there. Period 2, that's row 2 in the periodic table. Homonuclear, meaning both nuclei are the same. Diatomic, there's 2 of them. Molecule, they're bonded together. Molecules made up of 2 atoms of the same element. So let's look at lithium. We're looking only at valence electrons. So lithium has 1 valence electron. It's in the 2s orbital. And here's the other lithium atom, 2s orbital. When we combine those, same thing happens as with the 1s. We get a bonding orbital, but now it's sigma 2s, and we get an antibonding orbital, sigma 2s, sigma star 2s. And we've got this electron and that electron. We put them in here, and we get 2 bonding electrons, no antibonding electrons. So we get 2 minus 0 divided by 2. We have a bond order of 1. Lithium-2 is predicted to exist, and it does in the gas phase. Any questions?
Is there always antibonding?
Yes. There's always, if there's a bonding, there's an antibonding. And so it may be empty, but it's there. If we look at a homonuclear molecule of beryllium, Be, beryllium has 2 valence electrons. They're in the 2s orbital. So here's our sigma 2s and our sigma star 2s. This one also has 2 electrons. When we fill these up, we get 2 antibonding, 2 bonding. So this is 2 minus 2 is 0 divided by 2. Bond order of 0. Doesn't exist. Predicted to be unstable. And experimental observations. You can try to make it, but it's not going to stick around. It's going to come apart because there's no reason for it to stay together. How sad. It's an element. Beryllium atoms are fine, but a beryllium diatomic molecule, not so fine. Beryllium is not one of the 7 diatomic elements.
This is just to find that
No, this is not just to find diatomic elements. This is to, what is the point? What's the point of this? Why are we doing this? It's just to torture you. We invented this just to torture you. Specifically you. Yeah. To understand how molecular orbitals work. You're in this class, you need to know it. Question?
So beryllium and oxygen both have full 2s orbitals. Why is oxygen diatomic and beryllium's not?
We'll get to that. Patience. We're working our way up. Let's look at B2, boron. That reminds me of Bananas in Pajamas. Did you guys ever watch that? Bananas in Pajamas? There was B1 and B2.
That was legit.
It was. My son Zach, who's probably about this, he's 19, he had a Bananas in Pajamas birthday party.
Like recently?
No, when he was 2. When he was 2. Okay, sorry. When we look at B2, we're combining the 2p atomic orbitals. And we're doing this in pairs. So we're taking the 2px of one and the 2px of the other. And we are adding these in phase and out of phase. And so in phase, the parts between add together constructively, and this gets bigger. And when it's out of phase, these cancel each other out and get smaller. So this is anti-bonding. That's not going to contribute to these guys staying together. And this is bonding. And so just sort of, we assign this, this axis between the two atoms, the internuclear axis, we say that's X. And so then Y would be up and down, and Z would be in and out of the plane of the screen or board or whatever you're looking at. So this combination is going to be symmetrical along this bond axis. And so this is also a sigma orbital. Sigma is symmetrical around the bond axis. Pi is not. Pi is the other. So this is sigma 2p, and that's sigma star 2p. The remaining pairs of orbitals also get added together, but they're going to look a little differently. So here's py, and when we add these two in phase, we get a big negative one over here and a big positive lobe over there. Is that going to contribute to bonding? Is there electron density between the two atoms? Yes, there is. So here's one atom, and here's the other atom. All of this electron density is between. But this is a pi orbital now because it's not symmetrical along this axis between the two atoms. The anti-bonding is going to create a big node in between here, and then you're going to get these little balloons out here. So you're going to get, for the Y, you're going to get this. You're going to get a pi 2p and a pi star 2p. And for the Z, you're also going to get a pi 2p and a pi star 2p. Because these are parallel to each other. These guys formed sigma bonds because they were in a line. They were overlapping end to end, essentially. That just didn't feel real good, but do you have any idea what I'm talking about? No. These guys are aligned along the same axis. These are on the same axis, and so they're end to end. When they overlap, they form a shape that is symmetrical around this axis. So let me draw on this. So we're talking about this axis here, between the two. If I take this and turn it and look at the end, I'm going to see a little bit of red here, and then I'm going to see blue. Because the blue is bigger, and so it kind of sticks out over. That's really, looks like a strange eyeball, but looking, I'll draw a strange eyeball. So here's, you're looking this way. There's someone with an arrow coming out of his eye. Looking this way, you're going to look at this little red lobe, and then you're going to look through, and this is symmetrical. Do you see that? It's symmetrical. It's a cylinder, sort of. It's symmetrical. That makes it a sigma bond. These guys, if we look at those in the same way, looking this direction along the axis, what we're going to see is a piece over here and a piece over here. They extend from one atom to the other, so they're between that two atoms, but they're not symmetrical around this point, this line. And so that's a pi orbital. So this is, I'm sorry, pi, well, yes, an orbital. This is pi 2p and pi star 2p. And the only difference between the py's and the pz's is that the pz's would be at right angles. So this would be the y, and this would be the z. Is that any better? Not really. Okay, well, let's just plunge ahead, and hopefully some of it'll work. So here's the pz. It's going to have the same energy. It's only different in orientation. So here we've got these guys up and down instead of in and out. And so we get a bonding orbital. This is going to hold them together, and this is going to drive them apart because there's no electron density in between. This one has no electron density directly in between, but this electron density here is still holding these together. It's just not immediately in between. The energy ordering for these molecular orbitals from the 2p, unfortunately, is not the same for all molecules. And so they compute this, and we're not going to worry about that. What we are going to worry about is that boron, carbon, and nitrogen have one order, and oxygen, fluorine, and neon have another. So boron, carbon, and nitrogen are the first three elements in that P block. Oxygen, fluorine, and neon are the second. And how do you remember which one's which? Be careful now. So boron, carbon, and nitrogen have one ordering, and the others have a different ordering. The usual ordering is this, where we have the bonding, sigma bonding, pi bonding, then pi star, and then sigma star. That's normal. So that's the expected order. So the two S's overlap, and we get a sigma 2s and a sigma star 2s. When these p orbitals overlap, we do not get just two different energy levels, because the ones that overlap end to end are going to be lower in energy than the ones that are overlapping side to side. So we get a sigma 2p that's got the lowest energy. It also has the highest energy for the sigma star. It's symmetrical. And then pi 2p bonding and pi star 2p antibonding. This is what we expect. Boron, carbon, and nitrogen do not do what we expect. And so that's why we say, be careful now. We have to do these guys a little differently. So there's a flip in the order here. The sigma and the pi have switched. So this is like one of those Sesame Street things. What's the difference between these two pictures? These two have switched order. Let's make that red. The order has changed. This one has the sigma 2 pi at the bottom, and then the pi 2 pi. Start over. Sigma 2p, pi 2p. This one has the pi 2p at the bottom and the sigma 2p in the middle. The top two are the same. So that's something you have to remember. Everybody was begging for more complicated. Like, can we do nitrogen and oxygen and blah, blah, blah? Yeah, we're doing nitrogen, oxygen. No, it was you and it was him. It was the other Jose. Okay, so here's what happens with boron, carbon, and nitrogen. We get the sigma 2s and the sigma star 2s. And these split apart more than we expect. And then the sigma 2p and the pi 2p are reversed in order from what we expect over here. So this is the part that you have to remember. There's more mixing of the p's and the s's. It is confusing, I'm sorry. It will be on the... Well, let's get through it and then we'll get to what you need to know. Okay. The reason that we get this splitting is because boron, carbon, and nitrogen have a lot of interaction between the 2s and the 2px orbitals. And so the order ends up switching. And oxygen, fluorine, and neon have little interaction between those, and so the orbital stays the way we expect. If we look at the bond order here is there's 2 electrons in this bonding orbital and 2 here, so that's 4. And there's 2 in the anti-bonding orbital. 4 minus 2 is 2, divided by 2 is 1. Bond order of 1. This one, we have 2, 4, 6 electrons in bonding orbitals and 2 in anti-bonding orbitals. So 6 minus 2 is 4, divided by 2 is 2. And so this has a bond order of 2. And here they're also showing us the bond energy and the bond length. The bond energy of this boron-boron bond is 290. The carbon bond is 620. This is greater energy, stronger bond, higher bond order. And the bond length goes from 159 picometers to 131. Stronger bonds are usually shorter bonds. They're held together more tightly. And so we see that as the bond order gets larger, the bond length gets shorter and the bond energy gets higher. And over here, oxygen has a bond order of 2. It's got a high bond energy, a short bond length. Fluorine has a bond order of 1, and this is lower in energy and longer in length. And neon 2 has a bond order of 0. It doesn't form, and so we can't calculate it. If you do these guys with this ordering, you don't get the right bond orders, and it doesn't match up with the energies and the lengths.
And these are sets?
This is what these guys do, yeah. So, I mean, let's look at oxygen. Well, it really helps to, we'll just, oh, interesting.
Oh, no.
Link is broken. We know from experience that oxygen is paramagnetic. We learned about paramagnetism. That means that we have some unpaired electrons, right? In the Lewis model and the valence bond model, oxygen has no unpaired electrons. That's a problem because oxygen is paramagnetic. Here's the Lewis model. Everybody's paired up. Here's the valence bond. It should also be called balloon art model or something. These are paired. these are paired, these are paired, these are paired, everything's paired up. It does not explain the paramagnetism of oxygen. Let's just go back to this. Here is the molecular orbital explanation of oxygen. And what do we have here? We have 2 unpaired electrons. This predicts that oxygen is paramagnetic, and it is. And so this all by itself makes molecular orbital theory better than valence bond theory or Lewis theory. It's also more complicated, isn't it? Sadly, the more useful a model is, the more complicated and hard to understand it is. So let's do this example. Draw an MO energy diagram and determine the bond order for the N2 plus ion. And do we expect that bond to be stronger or weaker than the N2 molecule? And is N2 plus diamagnetic or paramagnetic? Okay, what atomic orbitals are nitrogen's valence electrons in? 2p and 2s. So there's oops. Oh, that's not going to work. Let's see. That's better. Good enough. So what kind of electrons do we have in here? How many electrons in nitrogen? Valence electrons? 5. So we've got 1, 2, 3, 4, 5, right? This is N2 plus, so then over here we need to give this guy just 4. So this is N plus, and this is N. And this is the 2s orbital, and this is the 2p orbital. Now, these are the atomic orbitals, right? Atomic orbitals over here and over here. And then in between, we're going to put the molecular orbitals, and I'm going to hope I can fit them in. So when the s orbitals overlap, what happens? We get 2 molecular orbitals, right? One is going to be bonding and one's going to be anti-bonding. And so this will be sigma star 2s, and this will be sigma 2s. It's harder than it looks. Ugh.
Can we just follow that order that we already know from here? For N?
Can you just copy the diagram? Yeah, but what if you don't have the diagram to copy?
Well, I understand.
Yeah.
I can
Yes. And so then when these guys overlap, we get a sigma bonding and anti-bonding and 2 pi bonding and anti-bonding. And the sigmas are the lowest and the highest, or are they? This is nitrogen. Be careful now. This one has the bottom 2 flipped. So down at the bottom, what am I drawing with? We're going to have the pi 2s is going to be, sorry, pi 2p is going to be here, and the sigma 2p is going to be here. Those are the bonding orbitals. And then there's just not enough room. And then this is going to be the pi star 2p. And then up here will be the sigma. Yeah, try to draw sigma with a box tool. It doesn't work at all. 2p. They're not spaced out as they should be. This orbital and these two are switched because it's nitrogen. Be careful now. Those are the three that you have to switch these bottom two. The top two stay the same, these two s orbitals stay the same. So now we take our electrons. We have 5 over here and 4, so we've got a total of 9 electrons, and we're going to fill the orbitals from the lowest to the highest. So there's 1, 2, 3, 4, 5, 6. They're going to take their own orbital if they can. 7, 8, 9. It's N2 plus. It only has 9 electrons instead of 10. Valence electrons. And then what's the bond order? How many electrons in bonding orbitals? Well, there's this one. There's 2. And this is 6, and 1 is 7. So 7 in bonding orbitals. How many in antibonding orbitals? Just 2. And that's divided by 2. So 7 minus 2 is 5. So we get 5 halves, or 2.5. Is that stronger or weaker than the N2 molecule? Like, well, we don't remember what N2 was. Well, N2 would have 1 more electron, right?
Yeah.
So it would be 8 minus 2, because that extra electron would be in a bonding orbital. So N2 would be 8 minus 2 over 2, which would be a bond order of 3. And this one up here is N2 plus, which is the one we're supposed to be looking at and comparing. N2 plus. A bond order of 2.5 tells us this bond is weaker than the bond in nitrogen, the molecule. Now, the blue one is for nitrogen, the molecule. We leave the blue one out to think about, is N2 plus paramagnetic or diamagnetic? Does it have unpaired electrons? Yes. It's paramagnetic. Any questions? Not necessarily. Not all ions will be paramagnetic. You have to look at the whole molecular orbital energy diagram to figure it out. So now we're going to look at heteronuclear. So 2 different atoms. So this is one of my favorite molecules. No! NO, it's all caps, it's yelling. No!
How does that work out with N by itself, or when it does it with its own N, and those with the sigma and the pi? Now you're using N and O, which are...
Yeah, we'll get to that. He's asking, well, N was be careful now, the orbital order was flipped and oxygen isn't, and how does that work? I'm getting to that. So oxygen is more electronegative. That means its atomic orbitals are lower. And when the atomic orbitals are different in energy, the lower one contributes more to bonding orbitals, and the higher one contributes more to anti-bonding orbitals. And so we see this, here's the oxygen. Its atomic orbitals are lower in energy than the atomic orbitals for the nitrogen, which are a little bit higher. And so when these combine to form the sigma star and sigma, they're not split evenly. This one has more of an effect on the bonding, and this one has more of an effect on the anti-bonding. So this one's a little higher than we expect, this one's a little lower. And the oxygen, I think, is going to control this business here with the, I think probably the rule of thumb would be if it's something besides boron, carbon, and nitrogen, you go with the normal order. Like if you had boron and carbon, or boron and nitrogen, or carbon and nitrogen, they're all in that be careful now group, you'd have the unexpected orbital levels ordering. But here we've got a regular one, oxygen, and so we're going to go with the regular molecular orbitals. So nitrogen has 5 valence electrons, oxygen has 6. And so they fill in 2, 4, 6, 8, 10, 11. And so what is the bond order for this one? We've got 2 in the bonding here, and 2 is 4, 6, 8. So we've got 8 in bonding, writing with the eraser. And anti-bonding, we've got 2 here and 1, 3. And so we get 2.5. Pardon me? When we draw these molecular orbital diagrams, we always have one atom on one side and one on the other. We draw the atomic orbitals first, and then we combine them into molecular orbitals. And we're just going to do 2. We're not going to go to 3 atoms. Well, these, it doesn't matter which one of these. Is that what you're saying? Which one of these to put in? We're going to fill from the bottom up. They're going to go lowest energy. This one's lower, so it'll pair up, and this one's lower, it'll pair up, and this one. And then here, they would fill 1 here and 1 there. That's Hund's rule. Then they would pair, and then they'll go up to the next level. There's a question in there, but it can't quite come out, huh? Let it rumble around. Isn't this fun? Hydrogen fluoride. Fluorine is really electronegative. Its 2p orbitals are lower in energy than the 1s orbital of hydrogen. And so this does a weird thing. One of the 2p orbitals combines with hydrogen's 1s orbital, and so we get this sigma and a sigma star. And these two have nothing to combine with, and so they're just going to sit here uncombined. We get a total of 6 electrons, and so they're going to fill up this way. Use molecular orbital theory to determine the bond order of NO. And this is why it says do a different molecule, because we just looked at that one. I made some notes to myself, but then I didn't look at them. So how about we do FO? Or let's do OF. Of. Let's do of. Do you really want to do 2? I don't really want to do 2.
I want to see how it's done. I want to see NO for the process of How about we take paper, rock, scissors?
Paper, rock, scissors. Let's do the lab.
Yeah.
Let's just do of. Okay. I really just need some sort of a template or something here. Okay. So here we've got oxygen, and here we've got fluorine. And we've got, I'm just going back to my stupid little boxes. And we've got 2s, right? And they're going to make the sigma star 2s and the sigma 2s. So these two orbitals are the linear combination of these two orbitals, 2s. And then we have the 2p orbitals, right? And they are higher in energy. And we're instructed to use the energy ordering of oxygen, but between oxygen and fluorine, it's going to be the regular order. And so we're going to have a sigma 2p, and then we're going to have the pi 2p, and then we're going to have the pi star 2p. Aren't you glad I brought candy today?
No.
There's candy. Can't you hear all the crinkling? Here, give the man some candy.
That's a big man. He's gonna need that whole thing.
Yeah, it's okay.
I've been getting up every once in a while.
Yeah, that's why Jose keeps getting up. He keeps getting more candy.
Well, you bring the candy to you.
Yeah, I guess it's like candy quietly.
Well, you know, when you find a good thing, you don't necessarily want to draw attention to it, right? Because then you have to share them. Okay. So this group of orbitals in here comes from the combination of these horrendously drawn 2p orbitals. How many valence electrons does oxygen have?
Wait, shouldn't oxygen be lower though?
We're not going to worry about that. We tell you about that, but we don't expect you to necessarily take that into account when you're drawing these things.
So no test, we won't be marked down. I want to hear you say it. You know, I want to hear you say it.
I'm not saying anything.
You just said it.
So 6. 1, 2, 3, 4, 5, 6. How many valence electrons does fluorine have? 7. 1, 2, 3, 4, 5, 6, 7. This part will most likely be multiple choice, and so it's picking the correct energy diagram, which is so much easier than drawing them. So between these two atoms, how many valence electrons do we have? A bunch. 6 plus 7 is 13, right? Just checking because my head calculator's busted. 13. So we're just going to, we drew these guys, we're just going to fill them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, big fat hen, 11, 12, 13. 6 plus 7 is 13. Because 6 plus 6 is 12, and 7 is one more than 12, so 6 plus 7 is one more than 6 plus 6. 13. That's what they do now in elementary school. It's actually awesome.
I still would have done that when I was young.
Right? Okay, is this paramagnetic or diamagnetic?
Paramagnetic.
Paramagnetic. We got this guy.
That's all I know so far.
Hey, it's something. It's something. What I find confusing about the whole paramagnetic, diamagnetic, is para makes me think they're all paired up. That's not what para means. It's not all paired up. Diamagnetic, di means two, they're all in twos.
This makes more sense now that you did it. Because you're saying that on the sides,
Mm-hmm.
that you fill in the valence electrons.
Yes.
You didn't say that earlier. I was confused with the no. On the no.
Okay.
Can you go back?
I can go back to the no.
So it makes sense now. You didn't mention that. Yeah.
So,
nitrogen's
yeah,
five, that's
this
on the
is,
side, it's
this
five.
is nitrogen, and its valence electrons in its atomic orbitals, which we learned a long time ago. And this is oxygen with its valence electrons in its atomic orbitals.
And then in that
And then in the
bottom
middle, we have the same number of electrons, we have the same number of orbitals, but the orbitals are combined and they're new. They're different shapes, they're different energies, same number of electrons. And we fill them from lowest to highest. So here's, yeah,
that makes sense.
we've got 5, good, it made sense to somebody. We have 5 from nitrogen and 6 from oxygen. That's 11 electrons. And so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
See, now that makes sense.
Good. So I've got one person on my side. Anybody else? He got it. At least part of it. So it's good. It's all good. Okay.
You need to bring candy more often.
I need to bring candy more often. So when we look at ozone, here are the Lewis structures for ozone. There's resonance because we have a double bond and a single bond, and it's actually that they're in between. Valence bond model can't handle that either. You can have the double bond here and the single bond here, or vice versa. It cannot do the resonance. But guess what molecular orbital theory can do? It can show the combination. We can get those pi molecular orbitals forming through a combination of 3 2p orbitals and being delocalized over the entire molecule. So we end up with our 1.5 bond between each.
Will we be expected to be able to draw
You
this?
do not have to draw this. And then there's benzene. Benzene's cool. Benzene, Lewis model looks at this as resonance with these double and single bonds going back and forth. We understand that it's in between. Molecular orbital theory can delocalize those pi or electrons over the entire molecule. And this is consistent with experimental data that shows that benzene has 6 identical carbon bonds. They're not double, they're not single, they're not oscillating or anything like that. They're the same.
What is delocalized again? What does that mean?
Delocalized. Well, localized means it's in one location. So localized, this would be a sigma bond and a pi bond. That's what a double bond is made of. And the pi bond is between these 2 carbons. This is showing that the pi bonds, all 3 of these pi bonds, are spread out over the whole molecule. They're not just between 2 carbon atoms. That's delocalized. They're spread out over the whole molecule. The end.